Okay, now officially welcome everyone to lecture number 3 in computational transportation. The main goal of this lecture series is twofold. One, to get you up to speed in operations research in case you haven't had a bachelor lecture about this. And second, using this lecture to show you the basic concepts of transportation problems. So problems where we need to transport things or people or services in an area. And in operations research, we usually have 3 steps. We look at one particular problem, application from the real world. We describe it in a mathematical model, and then we apply algorithms, heuristics, optimization tools to find good solutions. And then there's always the way back. If we found a solution in theory, looking if it works in practice. And last week, we already got one glimpse on this process. We looked at location planning. In the initial example, we had some burritos to sell. We modeled it, not really, but later we modeled a similar problem of location planning. And we learned about potential ways to solve it, pre-processing, simplifying the problem, and then either enumerating the remaining parts or at least conceptually a branch and bound where we simplify the problem, look at parts of them. So some sort of cases, if in that case, try this, in that case, try that. But we didn't really solve it. So you got the first idea of the 3 steps. And today will be the last lecture where we do not really look at the 3 steps, but at one in particular, and that is modeling networks. So in transportation, we usually operate on a network. This could be a street network if we use cars or bikes or trucks. It could be a railway network. It could be an air network if we have airplanes. It could be a sea network if we have vessels. But networks are more general. Networks do not only depict connections between locations, but can also show logical or abstract relations. For example, in the first slide, again, this one is very slow. Okay. Of a network, we will talk in the following a little more about this. But here, the arrows in the network, or later we call them edges, depict rather relationships of flows of goods between production plants, major customers, distribution centers, and suppliers. So here it's not about distance or travel time, but it's about how much capacity do we have, or how much do we need to ship between, for example, this supplier and this production plant. So we will talk about areas where network models are applied, and then we define a lot. So what is a network? What can we measure in the network? How are the components called? How are specific networks called? Especially, we then look at weights in networks. What do they represent? A weight is something that's on one of these arcs or edges. They are called, they represent different information, and then some properties in these weighted networks. So network modeling is not necessarily based or only for transportation. So many real-world problems can be modeled as network models, but especially in transportation, we have a direct connection. So if we have a road network and we have customers we need to deliver parcels to, we directly have a network problem we need to model via a network model. So some examples are traffic systems, airports, central stations, and bus stops. For example, we have a set of bus stops, and we have connections between them indicating how lines progress in the system, and the weights on these could represent either the distances or other things like the expected demand for this combination. So we could say this is a physical network. Others, hierarchical distribution systems, we have maybe one factory, or we have Amazon, the headquarter, or the head facility where all the goods are stored, and then we have hubs where the goods are delivered, and then we have maybe final stores or parcel boxes or final customers where the deliveries take place. And then we have a hierarchical network showing which hubs are connected with which stores and so on. So consumer goods with central and regional warehouses like Amazon. We have networks where we have collection distribution systems where there's not hierarchical, but it's all more or less on the same level. So parcel services with depots and hubs, where we can bring something to a hub, but we can also collect something from a hub. And then we have local supply and disposal networks. That's very often the ones we're looking at if it gets more operational, where we try to supply our city with parcels, or we want to get rid of waste in the city. We have on the edges, we have the amount we need to collect from a street. This is all transportation, but others, I didn't change the slide, by the way. So internet, electricity are also networks where we have servers, where we have other hubs. And if one of the power lines breaks, the network is disconnected. Telephone network, so this should be the one that will fail next, but I think no one cares anymore with telephones because we all have, actually telephone, WhatsApp already worked. Yesterday or 2 days ago, WhatsApp also didn't work. So this is some sort of prophecy of what will happen. Anyway, now we get a little more detailed, and we start with 4 examples to show you different types of networks. The first one is a physical network where we have vertices. Vertices are these nodes, and we have edges, sometimes also called arcs if they have a direction. And we have weights, that's information on the edges. And here, this is a road network example. We are here, and every vertex gives us a city. Every edge is maybe a direct traffic connection. And the weights are the distances. So if we go to Autobahn A2 from Magdeburg to Hanover, we travel about 146 kilometers. To Berlin, it's 153. And we cannot get to Halle, at least in this example. I think they're currently constructing the highway also. So it might be extended, the network. But you see, it's not possible to have direct connections between all locations. You always have some intermediate nodes. On the other side here, we have a air traffic network where the vertices are again locations. San Francisco here, Düsseldorf, and then we have some additional edges with all have some information, and that's Frankfurt, for example, has the star for Star Alliance. I don't know what these represent. And here, the edges give us routes between San Francisco and Düsseldorf. And the information on these are not the distances, but the provider of the service. So we see here on this left-hand side, we have very nice numerical data, which we can aggregate, sum up. On this part, we have rather abstract data, but we could use this for example, to find a trip between San Francisco and Düsseldorf with one specific airline or with a group of airlines, because Star Alliance is a group, to save a price or to enable seamless transition. Next example for a network is for procurement and delivery. Procurement means we need stuff. Delivery means we send stuff. And here, these locations in the network, they are not necessarily physically there. So these this plant doesn't need to be right in the center of it. It doesn't matter, because these arcs at this case, because they're directed, they do not represent distances, they represent flows of goods. So in this network, we have these suppliers, and we have 120 goods, whatever it is, to flow into this plant, 100 in this plant, and then we have 50 other goods going to this hub, 30 going to this customer, maybe, and so on. This is now simple with one type of flow, but they can have multi-dimensions, of course, if we have multiple commodities flowing around in our network. But in this case, the vertices are the partners in the network. The edges are where goods flow in the network, and the weights are the amount that flows. Similar to this part is within our, or let me start differently. There are also, or next steps are hierarchical networks, where we have a top. These are these two, and then we have a hierarchy going down. This could be a chain of command in companies, but here it's a so-called Gozinto graph for production planning, where we have a hierarchy of products we want to produce, like semi-finite products and some raw material. And this graph tells us how much get of these raw materials into the semi-finite products, semi-finished products, and then to the final finished products. And we can use this for planning what we need to order to produce these two products. Let's assume we have to produce 100 of them and 500 of them. Then this graph tells us what we need to in raw material to produce it. So here, vertices are objects, material we need to produce. The edges are the order in what comes first and where does it go to, and the weights are the quantities, how much gets into this. So you see, while in transportation we often assume a network is just locations and connections, a network can be a lot of things. And one more complicated example is this one, and here you learn a little bit of German on this slide, but not that much, so we will survive. And this is vehicle scheduling in public transportation. So what we have here is a so-called time-expanded network. We only have two stops, stop 1 and stop 2. And here we have some demand profile for public transport. And here, this is the time of day. And this demand profile tells us what public transport trips I need to satisfy for these two stops. In the beginning of the day, we need to satisfy demand going from 1 to 2. In the middle of the day, we need to satisfy demand in both directions. Maybe this stop 1 is a residential area, stop 2 is a working area. So in the morning, everyone wants to go to work. And then we need to have, in the afternoon, 2 flows back, so a lot, maybe because everyone wants to go home. And then we have a final trip back. I don't know why. Maybe the restaurant district is also at stop 2. And this network tells us over time and space what we need to satisfy. And based on this network, we could have a solution, which is also represented by this network, where we have two buses going. This is the first bus, this is the second bus. First one goes this way, waits, goes back, then has an empty ride. This is called Leerfahrt. Then travels back, waits, and then go back. And the other bus starts at stop 1, goes to stop 2, waits, and goes back. So a totally different way to think about this network type, where suddenly even though we only have 2 physical locations, since we expand this network in time, they reappear very often. So our network has actually a lot of nodes and a lot of vertices and a lot of edges. Some of you may have already heard my other master lecture on approximate dynamic programming, where we had a decision tree, where we make subsequent decisions over time. This is relatively similar, where we also have a network to model decision-making over time. There we also had stochasticity, we don't have it here. So having a network is fine, but why do we need such a network model? And there are a lot of questions we can answer. So in the first lecture we had, or actually last week, we had a network of potential locations to open up a new bike sharing station. So it was location planning, but once this, or other questions are often about shortest cost minimal path. So how can we get through the network very quickly, or shortest cost minimal tours? How can we visit all vertices in the network at cost minimal, or at minimum cost, or all edges? And cost are often associated with the weight, but cost does not need to be necessarily distance, but the weight can represent many other things too. So, for example, we are looking for a set of vertices to connect all vertices, or we search for a tour over a given set of edges. So we want to visit all edges in the system. That could be in waste disposal. Assume you have a waste disposal company, and on one day, half the city puts out these trash cans. Then you need to collect them. You need to drive through all streets. And here we're looking for a tour that doesn't that unnecessarily visits some streets more than one time, which is in reality not possible because we have one-way streets or dead ends, so we have to go back. This would be one common question. Other direct paths between 2 not adjacent vertices. Assume we want to go from here to Kiel. Then we want to have the time minimum path from Magdeburg, likely over Hanover, Hamburg, and then Kiel, but it is not necessarily always the case because we have traffic jams. Or a tour over a given set of vertices. This is a classical problem, traveling salesperson problem, vehicle routing problem, where we have to visit a subset of vertices, a subset of locations cost efficiently. So different questions in our network. And in reality, there are lots of additional constraints we need to consider or additional questions. So if we find a tour, sometimes we have vehicle capacities. So even though we could visit an additional customer easily, our vehicle's full, so we need to consider this. Or we have time windows in many of these grocery deliveries. We have time windows, so a customer can select, I want to get my delivery in the morning, and then we need to consider this. And even though your neighbor also ordered, this neighbor ordered in the evening, so suddenly we cannot visit both of you together. Loading and unloading are also called pickup and delivery. So for some problems, we need to pick something up first because we can before we can drop it off. That makes the problem more complicated. Or with uncertainties, That means we may have uncertainties in travel time, we may have uncertainties in is the customer there, or subcontracting, we might outsource some of our jobs. The list is endless, and in this part of the lecture or of the master lecture series, we won't touch all of them. We just give you the foundation. In the other parts, we then zoom in a little more. Okay, now we get lots of definitions. We'll later use and need. Because we never really defined what a network is. So we start here with the simplest network there is, a so-called undirected network without weights. So an undirected network seen here has vertices. These are the nodes here. This network has 6 vertices. Connections between them, they are called edges. This has 1, 2, 3, 6 edges. And here the vertices have numbers, 1, 2, 3, 4, 5, 6. And the vertices, they don't get their own names. They are defined by the vertices they connect. So here, this edge is called 1, 2. This one is called 2, 4. And the rest is written down here. Such a network doesn't need to have weights. This could be, for example, a neighborhood network indicating which 2 nodes are neighbors. These nodes could be countries, and this one would just indicate they are neighbors, and this one would indicate they are not. Or these are entries in a social network, and you could indicate if they are friends or if they are following each other. Or I don't know how you connect on TikTok, but this would be, the 2 are connected, these 2 are not. So something where we just have a binary relation between 2 items. So these 2 vertices. But we already can do a lot with this network, and we can tell a lot about this network, and this is shown here. So a network, every vertex has a degree, and that means how many edges go into this vertex. So let me quickly jump back. This one here has a degree of 1 because only 1 edge goes in there. This one has a degree of 4. This one has one of 3, and so on. There are some maybe isolated vertices. They are called, they are isolated if they have a degree of 0. In a social network, isolated means you don't have friends. In countries, it means you do not have a border with someone else. But in general, we can say that a vertex that has no connection at all. So our office last week was isolated from any power. Complete network means all vertices are pairwise adjacent, meaning they are all neighbors. So this network, everyone is connected, and there is a special relationship between the number of vertices, n, and the number of edges, m, in such a network. So if we have only one node, one vertex, then the number of edges in this network is 0. 1 minus 1 divided by 2 is 0. If we have 2, the number of edges in the network is 4 minus 2 divided by 2, so it's only one connection. And then if we increase the number of vertices, this number of edges increases exponentially. Or no, not exponentially, but polynomially, yeah. But it increases a lot. So a complete network gets complicated relatively quickly. In a network, we can define a walk, which is just a finite list of vertices that are connected, actually. So a walk here could be somehow this is 1, 2, 5, 4, 2, 5, 6, because in a walk, we can visit vertices more than one time. And a more limited version is the path, where we are allowed to visit each vertex at most one. And that's the next part here. So a walk without multiple vertex visits. We're usually searching for a path, because if we visit some vertices more than once, it is potentially more costly than just visiting them only once. And we have a cycle, which means it's a walk or path. So it could be both, that starts and ends at the same vertex. So our classical tours, visit all customers and then come back, is always a cycle, and very likely it's a path. But it can also be a walk. So in a cycle, you can visit vertices more than once. We can say a vertex is connected to another vertex if there is a path between them. So it doesn't necessarily be directly adjacent, so a neighbor, but it can be over several additional vertices. So if we look at the street network in Europe, between Magdeburg and Copenhagen, it's likely not, they are not adjacent, but they are connected over the road network. We look Magdeburg and Mallorca, they are likely not connected over the road network, but over a different network. A connected network is then if all of them are connected via a path. And components in a network are parts that are connected with each other. So in a fully connected network, we only have one component, but we might have more components if this network is not connected. Next step from the network without weights is now the directed networks without weights. So this one has, again, vertices, but now also directed edges that are often also called arcs. And there are arrows indicated with arrows. So we see here, this is an arrow. And here suddenly it matters what comes first. So in an undirected network, the edge ij and the edge ji were the same. Here, ij indicates this goes from I to j, from 1 to 2. And this could, for example, represent a chain of command where we know who can command whom in this network. And usually this shouldn't happen. So we have an undirected edge actually represented by 2 arcs in such a network. But in general, in a there might be undirected relationships in adjacent vertices, also in a directed network. So every undirected network can be represented by a directed one by just duplicating the edges and making 2 arcs out of it, one direction, the other direction. But not every directed network can be represented as an undirected one. At least, so I tried. If you find a way to do this, this would be another way to solve this famous NP equals P problem, because some algorithms work on an undirected network way faster than on a directed network. Anyway, it's difficult to represent this connection in an undirected way. And I assume it's impossible. So maybe this was a short excursion. What you need to know from this is sometimes we have arrows, and then we have a directed connection. And in a street network, this could be a one-way street, for example. We cannot travel from 2 to 1, we can only travel from 1 to 2. Or in a network over time, this could be progress in time. So maybe this was an event that happened earlier than this one. But again, here we can travel back in time, and that's very unlikely, usually. Okay, if we have a directed network, we can define some additional things like the predecessors and successors. if we have such an arc or arrow, the predecessor is where we come from, the successor is where we go to. And for each vertex in our network, we can define a set of predecessors. How can we get to this vertex? And a set of successors. Where can we get from this vertex? They are often called P of I and SU of I. As with our other undirected network, we can also define a degree, which is now positive or negative. Positive means how many, let me check, successors, how many arcs go out. So degree plus is the cardinality of the successors. Negative means how many go in. So if you look at a chain of command, having a high positive degree is good because you can command a lot. Having a high negative degree is not so good because everyone can tell you what to do. And then we have NLO, similar to the other one, directed walks and directed paths. But now we need to look at the direction. So we cannot walk backwards in time or against one-way streets. So we need to consider the directions of the edges. And we also have components, and we could say we have strong components where all vertices are connected by a directed path. And weak components where they are somehow connected, but it doesn't need to be in the direction. So for example, this one, 2, is weakly connected to 1, and 1 is strongly connected to 2. Because we, if we ignore the direction, we could go to 1, but if we consider the connection, we can only go from 1 to 2. There are lots of problems where we can even go one step further and say that a network is bipartite. And that means we can divide it into 2 sets. And these sets are more or less distinct. One typical application is a transportation problem. We have maybe factories where we have supply, we have cars or whatever we produce, and we have car dealerships or some customers, they have demand. And now we want to ship supply to demand. And then we have the set of vertices here that are the supply set vertices, and we have the demand set, and they are only connected in this direction. So we do not ship between suppliers, we do not ship between demand. We have this part and this part. These are 2 parts and therefore bipartite. Another application is an assignment problem. Assume we are on a job fair, or we have some job applicants. We have 3, 4 jobs to fill and 5 candidates. Then the candidates could be on this part, on this side, and these could be the jobs, and an arrow could indicate which candidate is in general suitable for a job. But again, a candidate is not suitable for a candidate, and a job is not suitable for a job. So there are no connections between these individual sets. And there are several special properties of this. If we ignore directions, then cycles always have an even number of vertices. So a cycle would go from this part to this part, then against the direction back, and would always lead to an even number of vertices in each cycle. Path switch between the 2 sets. So if we have a path, we always go one set, the other set, one set, the other set. And for these bipartite networks, there are many very efficient algorithms. And the reason is that we often can solve these problems, even though they are mixed integer problems with integer variables, with linear programming. Also, again, a small excursion, because the matrices in these programs are very nice, so-called total unimodular. Okay, but for us, just that you've heard of bipartite networks. So they were all undirected, they were all without weights. And now if my slide continues, we look at weights for those networks. By the way, this lecture will be, because it's a definition lecture, and definition lectures are often a little slow. This will be not 1.5 hours long, because defining things is a little tiresome for me, but also for you. But we need this stuff to optimize later. Okay, weights in networks. So we had a network with vertices and edges. And now we can, to every edge, add a weight, or every arrow. This is often called a distance, dij, and here it's in R+, so in the positive real values, but it doesn't need to be. In street networks, distances are usually positive. If I travel from here to there, I travel a positive amount of time or distance. But in other more abstract networks, this could also be negative. For example, if you depict on a network the energy consumption or energy gain you get with an electric vehicle. If you travel up a hill, you'll probably consume a lot of energy. If you travel downhill, you might even get energy. So the energy consumption might be negative. So it's not about distance. It can be anything. In distance can represent a lot of different things. But you often see the word distance or cost in such a weighted network. But this represents, again, can represent a lot of different things. So we had a network before that was without weights, 2 components. Now we have 3 components. And D is a matrix, has an entry for every I and j, with I and j being vertices, or ij together being an edge. And if we don't have an edge between 2 locations in this matrix, we often have an infinite, or it's just not, it's no value at all. If we now look at the path, suddenly we can evaluate passes in the network. If we say a path from Vi to Vp is a list, first we go to V1, V2, V3, and so on until Vp. Then we can calculate the length of this path as the sum over the distances. So distance from Vi, V2 to distance from V2, V3, and so on. And then we already can maybe search for a shorter path than the one we currently have. So suddenly it becomes important where we go. In transportation, we usually have 3 types of distance matrix. So there could be the linear distances, the Euclidean distances between 2 locations. There could be distances in the road network. So usually we cannot directly travel from A to B. We have a road network to consider, or there can be travel times in the network because one street might be longer, but we can travel faster than another one. And we'll have a closer look at these 3 in the following. First is Euclidean distances. These are the easiest ones to calculate, but they do not appear that often in reality. So assume we have maybe ships on an ocean, or we have airplanes, or we have drones in the city. They do not need to consider any obstacles, but can travel directly as the crow flies. Then we can use these Euclidean distances. And this is just what we had last week, I think, too, the square root of the squares of the differences in the coordinates. And if we have a Euclidean network with Euclidean distances, this network is also complete. We do not need to take a detour of additional vertices. We can always travel directly between 2 vertices. In a transportation network, we can get, again, XY coordinates of cities or of customer locations. But then usually we do not have the Euclidean distances because they are very optimistic. So if we look at Euclidean distances, and sometimes I don't know, I think Google Maps did this here in Sachsen-Anhalt 1 year ago when I wanted to travel to Stendal for some reasons. Yeah, there was a PlayStation 5, and 1 year ago it was difficult to get. And okay, I have time, and maybe it's a little okay, but so they were every minute they were updating the system and telling you where you can get the closest one. And they told me Stendal, and it was only 100 kilometers. So I thought, okay, 1 hour, but it turned out to be way longer. Anyway, the other option was Dortmund or Dresden. So I thought it was easy, but Google actually cheated me. And the real distance, Google somehow calculated the Euclidean ones, the real distance were way longer. So, and that's usually the case, that the real distances in a network are often substantially longer than the Euclidean distances. There were some tests where they calculated or they looked at ambulance travel. So the advantage of an ambulance is that they do not need to consider traffic jams or stoplights, so they can somehow directly see how long they needed from A to B. And they figured out that for an ambulance, the distance they travel was about 1.3, 1.4 times the Euclidean distance. The other one here, great circle distance, we have a look on the next slides, but only briefly, because it gets a little messy, is we are on a globe. At least I think 99.8% think that we are. And on the globe, it's not Euclidean, but it's somehow circular. And this makes the Euclidean calculation way more difficult. And I will just show you the slides. So we have XY coordinates that are latitude and longitude. And if you had geography in school, you probably know this all better than I remember. And if we look at our globe, we have these coordinates on the globe. And if we now want to go from the north to the South Pole, we cannot really travel directly through the globe, but we need to have this circle. And because there are circles, to calculate this, we need trigonometry. That's on the next slide. Again, I won't go into much detail. It's also not part of any exam, but just it leads to a similar measure as the Euclidean distance, but not on a plane, but on a globe. And beside, we have cosinus and sinus cosine. We also have some arc cosinus. But anyway, what's interesting for us is that we now do this for Madrid and Berlin. So you see longitude, latitude for the two. The Euclidean calculation is not really possible. On this side, this would be, it's not really shown. Somehow the calculation, if we go directly from 1 to 2 with this big circle data, 1,800. And it would look a little bit like this. And we see that's actually also what Google Maps tells us, but not fully. So the distance is again longer, about 30% longer, I'd say 20 to 30% longer than the direct connection. It also has some sort of circle here. However, we see that we do some detours. We travel through Paris, which is there. So if you go through France, you usually cross Paris. So again, the street network is not as direct as the direct. So, but if we go by plane, this would be more or less what we fly. Okay. So finally, some things in the network we need also to give you something to do in your exercises. So creating the first exercise is a little bit difficult because we have lots of definitions, and exercises about definitions are not fun. So some properties. One is a triangular inequality. which always holds in the Euclidean plane, it's always better to go directly than compared to taking a detour. So dik, the distance from I to k, is smaller or equal than dij to djk. The detour is not shorter than direct connection. And for Euclidean data, that works. In road networks, it does not work all the time, because if you look at travel time, sometimes usually it's better to go on the highway first and then travel the highway and then go back instead of traveling a rural road between two cities. So it takes longer to traverse a kilometer in the city than on a highway. Other example, if you go by bike, if you want to go up a hill, sometimes it's better to go circular around it than try to get directly up the hill, or if you hike. But in most of our networks, because we often consider street networks, so in distance, the triangular inequality holds. In travel time, it does not need to hold, but if it doesn't hold, we can repair that. And how we repair this, we will learn in some later lectures. And this triangular inequality allows us to simplify problems. So if we look at the traveling salesperson problem you might have heard of, we want to visit all customers in a cost minimum, distance minimum tour. This triangular inequality tells us it's never better to visit a customer twice, because this would mean a detour. And in that case, at least in a complete network. And so we can simplify the model a little bit. Some other properties, symmetric versus abstract data. If we have an edge between I and j, we have a way from I to j and a way from j to I. So we have an undirected connection if we have Euclidean data, if we have geographical data and network data on roads, as long as we don't have. So I am pretty sure there is no road where you can only go one direction, but you can never go back, because otherwise you get stuck there. But usually you can go both ways. And the way is often the same. We have asymmetric data. This is not the case. Sorry, I mixed that up. You see, definitions. Okay, let me start this part again. So symmetric means the best way, or the best way from I to j is the best way from j to I. Okay, and this happens in all of them. But if we have asymmetric data, this is not the case. And symmetric means in our distance matrix, the distance from ij is similar to the distance from ji. Asymmetric means the distance might be very different. And now it makes sense, because we have one-way streets, and in one-way streets, we might get easily from I to j, but very differently from j to I. Or if we go downhill, very easy from I to j, but uphill, we might take a different tour. Another example here is in production planning. So in production planning, we often produce one product, and then we switch to produce the next product. And we can represent this as a graph, where each vertex is a product we want to produce, and each edge indicates with the weight how long does it take to switch from producing product 1 to product 2. And we want to find the shortest tour of, so all products are produced with minimum time of switching the product. One famous example is chocolate production. We have dark chocolate and we have white chocolate. And if you first produce white chocolate and switch to dark, the switching time is very limited. But if you switch from dark to white chocolate, you need to clean everything, and it takes several days. So in that case, we don't have symmetry, we have asymmetric data. where going one way from product 1 to product 2 is way faster than going the other way around. And the more abstract the data gets, the less symmetrical is our distance matrix. And can also be that the triangular inequality is not fulfilled anymore. So here, as an example, time-dependent consideration of transport networks. So if we look at a time-dependent network, maybe we have time-dependent travel times. And if we do that on aggregated data in 1 hour, the travel time might be different than another. So waiting and then going, which is more detour. Any time-dependent network, let's wait a little bit and then go. Might be faster. So this is the time then going here. So travel time in this hour is longer, at least in theory. So the more abstract, the weirder it gets and the more difficult also to solve these problems. Anyway, we will mainly focus on symmetric data and therefore on nicer, cleaner problems. Okay, and finally, some classification. We have land-bound networks, road and railways, and these usually only have a very limited number of edges. So if we look at a road network in the city, cities have about, I don't know, Magdeburg has probably about 30 to 40,000 locations of shops, of addresses. But I assume the number of streets is not, what was it, n square minus n divided by 2, but way fewer. Because in such a network, usually we only have local connections between vertices. We don't have a direct street from here to the train station, for example. Yeah. So, and to get from A to B, we use intermediate vertices. So we have several vertices on our way that could be traffic junctions in our network. And usually a planar embedding is possible. Planar or planar means we can draw a graph without crossing. So this is a planar graph. This one is still a planar graph. So this is a complete planar graph of degree with 4 vertices. But if we want to add a 5th one and want to connect all of them, suddenly it becomes not planar anymore because we have a crossing. In our cities, we usually don't have crossings. The crossing would be another vertex, usually where we can switch between the streets. And the number of edges is very limited. So if we have n locations in a city, then the number of edges is more or less lower equal 3 times the n or even 2 times the n. So if we have a sparse network with only a few streets. So if Magdeburg has about 33,000 locations, it has about 100,000 street segments at most. The opposite are sea and airbound networks. They are usually or theoretically complete because on an ocean we can go directly. We do not need to have intermediate stops except for refueling maybe. That's the reason for theoretically. Same is true for airlines. And therefore we have often many direct connections. There are some asymmetries due to wind and streams. So if you fly to the US, it often takes about 1 or 2 hours longer than if you come back due to the wind. If you go, I don't know, by ship, I don't know, I'm from the Baltic Sea, we don't have any streams there. Okay. And a little more on road networks. So if we look, let me check. If we look at distances, in a road network, we really represent the distances or we travel on the road. If we travel long distance, it's usually close to symmetrical. So if I go from here to Kiel, it's likely it takes the same time than going from Kiel to Magdeburg, except maybe if there's a traffic jam. But in general, in distances, if we really say distances, this should be the same. However, in local traffic networks, so in the city, the distances do not need to be the same due to due to one-way streets or other reasons. My favorite reason is UPS. UPS once had a perfect, or they thought they had a perfect routing tool, but in reality it failed miserably. And the reason was that they tried it in the US. And in the US, you have these classical city shapes. The reason we have a Manhattan distance because they look like this. And UPS assumed turning on a crossroad takes maybe half a minute, but it doesn't matter in which direction you go. However, in the US, if you want to turn right, it's no problem at all. I think you can always directly turn, but if you want to turn left, you need to wait a long time because there's lots of traffic coming down. So assume we are here and want to go there, or we are here and want to go there. We're here, we can directly go. And what UPS, because they realize turning left takes no time, what they're actually doing now is we're traveling 3 times right to go left. So suddenly this distance, not the time, is way longer than the other way around. So in a city, this matters. If we are long distance, then it doesn't matter that much anymore. And as I also said, the road network distances are about 30% above the geographical distances as the crow fly, Luftlinie. Okay. The distance-dependent weights on a network in general fulfill the triangular inequality. So if we look at a road network, it's always better, or the distance, the direct distance is always shorter, but the time may violate triangular inequality because of different traffic speed limits. Maybe finally, if you want to do this, how can we approximate our distances? We have digital roadmaps, we have Google Maps, which is rather limited because they want to sell the product. But there's OpenStreetMaps or others where you can get the network data. But if you're a company, then you might need some additional information which you have to pay for, or which you get maybe if you're lucky from the government, like truck closures, maximum bridge loads, or clearance heights. So if we look at Google Maps, we don't see that because our cars or bikes are usually not that high or not that heavy. But if you're a commercial transportation company, you need to consider all of them too, which are somehow enriching this distance matrix. So we might have additional matrices giving us more information. And then that's what we look in the other lecture in the summer semester. Often we have real-time information, traffic jams, or some road closures, which we get in real time and which we need to incorporate in our routing. Okay, so we made it. This was the last definition one. Next one, we have some minimum spanning trees or trees in networks in general, which in German sound way nicer because they're translated as exciting trees. For now, that's it from my side. Have a nice long weekend. So for the ones of you who are just arriving in Germany, we have a PhD student from Columbia here. Monday is a holiday. So if you want to shop, ideally shop tomorrow, because on Saturday people will go crazy. Okay. That's it from my side. Thanks for watching and see you next week.